This lesson is part 1 of section 9.4. Today we're going to be solving trig equations. We have 3 main objectives. The first and the last one are pretty simple ones. So our first objective is just to determine whether or not a number is a solution to a trig equation. The third objective is to be able to solve a trig equation using your calculator. Now the second objective here is really a huge objective. It's really difficult to explain all of the things that are involved in this, but basically you're going to solve trig equations by either factoring or using identities. Which means that you need to know and be able to apply all of the identities that were from sections 9.1 through 9.3. So that's why it's kind of a big deal, kind of a difficult objective there. So let's get started with objective 1 here. It asks us to determine if the following are solutions to the equation, the cosine of x plus sine of x equals 1. So obviously I'm going to be plugging in this real number pi over 4 into the function here. So cosine of pi over 4 plus the sine of pi over 4, does that equal 1? Well, cosine of pi over 4 is root 2 over 2, and the same with the sine of pi over 4. If I add those together, it does not equal 1. That ends up being root 2 over 2, 2 root 2 over 2, which simplifies to just root 2. Clearly not 1, so this is not a solution. Meanwhile, while we check pi over 2, so we input this into the equation, the cosine of pi over 2 plus the sine of pi over 2, let's evaluate and see if this is equal to 1. The cosine of pi over 2, remember this is up here, which means the cosine is 0. The sine of pi over 2, if it's up here, then that would be 1. So we have 0 plus 1, and that is true. So this is an example of something called a conditional equation. Okay, so it doesn't work for all real numbers. It only works under some cases. For example, here when pi over 2, or when you're inputting pi over 2, and in this example over here, obviously it did not work. So this is considered a conditional equation versus what we've studied so far, which are identities. So here we have the identity cosine squared x plus sine squared x equals 1. We know this works for all real numbers, so we don't even need to test pi over 4 or pi over 2. Yes, this will be a solution, and yes, this will also be a solution because this is an identity. Identity. I don't think I spelled that right. So what we're going to be doing is solving conditional trig equations. Now we might throw in an identity, in which case you'll have to recognize that it's all real numbers for the solution, but mostly we're going to deal with conditional trig equations. So for example here, it says consider the equation 2 times the sine of x equals 1. When solving any trig equation, you always want to just use sound algebraic steps. So in a normal equation, we would try to isolate x, and in this case we want to isolate x as much as possible, which means we're going to isolate this trig function, the sine of x. So I would divide 2 to get the sine of x equals 1/2. Now when I consider this, what I'm thinking of is what value of x can I plug in so that the sine ends up being 1/2. This is the short, right, side y value. So you think about in terms of a unit circle, there's one approach to take here. So I have a picture over here, a unit circle. So you can take this approach and think, okay, I'm looking for the short side, which would be closest to the x-axis, so that's in the pi over 6 family. Sine of pi over 6 is 1/2. I also know, however, that the sine of 5 pi over 6 is also positive 1/2. So I have 2 unique solutions here on the interval 0 to 2 pi. So we have to pay attention to with what they're restricting it to. So here it's restricted to the open interval 0 to 2 pi. So we have 2 solutions, pi over 6 and 5 pi over 6. Now in part B, the directions say find all real number solutions to the equation. Now the reason why all is bolded here is because if you think of this from a graphical approach, the sine function here, so this is a graph of the sine function in red. That sine function here continues, right, and it has a domain of all real numbers. Now I have graphed also. Okay, so in part B here it says find all real number solutions of the equation. Now all is bolded, okay, because there's actually an infinite number of solutions to this equation once we open up that interval from 0 to 2 pi to all real numbers. And that's because here if we look at a graphical approach of this, we have the graph of y equals sine of x, and then in green here the line y equals 1/2. Clearly you can see the intersection of these two curves is going to be infinite. It will intersect, I should say, infinitely many times. Now obviously it would take forever. You wouldn't ever be able to stop if you had to rewrite every single one of these points. So we kind of use notation here that helps us to write and kind of summarize what we're seeing. So we know that pi over 6 is a solution to this particular equation. However, we know that any time we add 2 pi to that value, right, we're going to get a new and different value that is also a solution to that equation, because this is a periodic function. Now, in order to show that we can add any value of 2 pi, or even take away 2 pi, right, multiples of 2 pi, I'm going to add the integer n to this. So n represents here any integer. Okay, so this represents all of your pi over 6 solutions. Now, we also know that 5 pi over 6 is another solution, so we write that as 5 pi over 6 plus 2 pi n as well. Okay, now you can think of that graphically as well. Okay, I'm sorry, with a unit circle as well. So that was a graphical approach. Here you're seeing a unit circle. Just think of this as pi over 6, and then if you go another rotation around, this has a coterminal angle, but you just added 2 pi to it. Go around one more time, so just basically the number of revolutions, you know, that you're taking, you end up with a coterminal angle. So here the emphasis is more in terms of I'm having trouble spelling today. Coterminal angles. Okay. Okay, our third approach is going to be using inverse trig functions and our calculator in order to solve some trig equations. So that's actually our third objective also, is to be able to use our calculator to solve some trig equations. Now off to the side I have this little note here about inverse functions. We did talk about this already, but I just want to refresh this. So here's the notation that we use for the inverse of cosine, the inverse of sine, and the inverse of tangent. I want you to make sure though that you realize that this is not an exponent. Okay, so a lot of times students will confuse this and think, oh, inverse of cosine, that just means 1 over cosine of x. That is not true. This is not equal. Remember, 1 over cosine of x is the secant of x, right? We know that is equivalent to that. That's a reciprocal function and not the inverse of cosine. So inverse cosine is an entirely different type of function. It actually has its own domain and range as well. And we'll talk about that actually in the next section. But for right now, we're going to talk about the fact that its domain is between negative pi over 2 and pi over 2. We'll talk more in depth about this, like I said, later on. But for our calculator, it's important to realize that it's from negative pi over 2 to pi over 2. So anyhow, we have our equation, the sine of x equals 1/2. Now if I want to isolate x, I can use an inverse operation to get x alone. That inverse operation is inverse sine. So I take the inverse sine function here on both sides of that equation. Here, this leaves me with x. That is actually going back to some of those identities that we talked about with, you know, fundamental inverse identities there. And that leaves you with just x. And on the right-hand side, I have the inverse sine of 1/2. So this is an exact answer, and then I can use my calculator to find that value. So let's whip that calculator out here. I'm going to type in second inverse sine here. And if I type in 1/2 or 0.5 here, I get that answer of 30. Now, you got to be careful because my calculator right now, if I go to its mode, it's in degrees. And if we look at our interval is in radians, from 0 to 2 pi. It's an open interval, but it's definitely in radians. So we want to go back, change our mode here to radians, and type that one in again. So second entry here. Now I clearly get a much different answer. So I have that the inverse sine of 1/2 is approximately 0.5235 radians. So this answer here, x is approximately 0.5235 radians. Okay, now we got to remember we got two solutions here in our previous, you know, look at this the same problem, right? When we looked at a graphical approach and when we looked at the unit circle, we get two different solutions. We get 5 pi over 6 and pi over 6. Now your calculator, like I said, it's going to be limited to giving you values that only fall between the first and fourth quadrants. So pi over 2 and negative pi over 2 here, this is basically the domain that your calculator is restricted to, because our function here, the inverse cosine, is restricted to this domain. So we actually have to use reference angles to find the other values here. So when you think of the fact that your other, you know, your sine function is also positive over here in this quadrant, so we just found our value here, pi over 6. Oh, I should also mention that you can verify that this is the right value here. If I literally type in pi over 6, I get the same value, 0.5235. Okay, so that's how you know that you're doing something correctly in your calculator. But anyhow, this other value here, this 5 pi over 6, how do I get that? Well, think about it in terms of a reference angle. If I want to find that other value, this here, reference angles, this is way back from chapter 7, but they're always in reference to the x-axis, okay? And they're always positive as well. So to find this other radian measure here, I'm actually going to have to take pi minus pi over 6, okay? Oh, I'm sorry, minus this 0.5235 in my calculator. So to find the value here, the approximate value, I'll take pi and subtract that answer here to get 2.61799. So we also have, remember, another solution here. X is also approximately 6179. And again, I can verify that this is in fact 5/6 pi. Okay, boom, look at that. So interesting. So this exercise here that I just showed you of finding an alternate value is going to be very important. Make sure that you understand what you're doing here. And if you need to go back and review reference angles, I think that was section 7.3 in our textbook. So you can go back and watch a little bit if you forget how to do that. Okay, so I want to stress to you that when you're solving a trig equation, you can use any methods that you would normally use in solving normal equations. So one of those strategies that you might want to use is solving by factoring. So I've got a couple examples here that we're going to solve by factoring, and we're going to answer also within respect to conditions A, B, and C. So let's start here in problem 4. Now in problem 4, I see tangent theta right next to a cosine of theta, and I can't really solve this unless I were to separate the tangent of theta and the cosine of theta. So I'm going to move that 2 tangent theta to the left-hand side here, and then I'll factor out the tangent of theta, which will separate cosine squared theta and tangent of theta. So now I've turned that into a product, and now I can use zero product property. So I have the tangent of theta equals 0 and cosine squared theta minus 2 equaling 0. Now I solve each of these equations independently of one another, so I'm going to focus on one at a time. So here in the left hand side I have the tangent of theta equals 0, so that occurs when theta is 0 at pi and at 2 pi, but remember we're answering with respect to these conditions here. So part A says only solutions within the interval 0 to 2 pi, and 2 pi is not included, so I'm not going to use that 2 pi here. Now when I look at the right side equation here, cosine squared theta minus 2 equals 0, I'm going to add the 2 to the other side and solve this equation here, which means I can square root both sides. So if I take the square root of both sides, I have the cosine of theta equaling positive or negative root 2. Now this actually has no solution, and the reason is, if you think about the cosine of theta, that function has a range between -1 and 1, right? Our range for the cosine of theta is from -1 to 1, which means that no matter what you plug in for theta, it can never equal positive root 2 or negative root 2. So there is, in fact, no solution to our equation on the right-hand side here. So we get no solutions from that. So let's go back to tangent of theta here, equaling 0, and answer with respect to all of these. So I've got, for part A here, theta can equal 0 or pi, and for part B, theta, we can include 2 pi, but remember that the tangent of theta has a period of pi, which means then your solutions are going to be 0 and pi n, and actually I don't even need to write 0 here because pi n includes that if n is any integer. So that includes 2 pi, 3 pi, 4 pi, everything. Okay, so tangent, the tangent function has a period of pi, which is why we're not using 2 pi k or 2 pi n. Okay, your book uses k a lot, so that's why sometimes I accidentally write pi k. So if you see me writing that, don't get confused. You can use any any variable you need to represent any integer. I just like to use n. Okay, now for part C, I'm going to take out a calculator here in a second. But let's just say that you haven't done any of parts A and B yet. Okay, so that you've stopped here, and you think to yourself, okay, I'm going to use my calculator now to solve both of these equations. So when you type this into your calculator, you're going to have to isolate that theta. So you need to take the inverse tangent of both sides, right? We end up with theta equaling inverse tangent of 0. So that's exactly what I would type into my calculator, so I've already done that for you, and I end up with just one solution of 0. So that's why you really have to make sure you understand that whole idea of reference angles, that there are multiple solutions even within the range 0 to 2 pi. So you have to, not just rely on whatever your calculator tells you, because it's only going to give you one solution here because pi is not within its domain. The inverse tangent function's domain, and we'll talk about that, in section 9.5. But that tangent function has a domain from negative pi over 2 to pi over 2. So it's only going to give you solutions, or calculator will only give you solutions that fall within this domain here, which means then that if you rely only on your calculator, you could run into some potential, errors and missing solutions. Okay? Okay, one last thing before we move on to number 5. Way back in the beginning of this problem, one of the things I've seen students do is divide out the tangent of theta right away, because they think, okay, I can get rid of that on both sides and I'm left with cosine squared theta equals 2. Now obviously we saw that the tangent of theta is where our only solutions came from, but this is a really bad move to make in just normal algebra equations. Like if I gave you x squared equals 4x, and you say, okay, I'm going to divide out that x, and then my solutions will be x equals 4, you're completely forgetting about the fact that if you factor this, you end up with two solutions, x is 0 and x is 4. So please avoid the temptation to divide out the tangent of theta or any function from an equation. You never want to do that because you eliminate potential solutions. Okay? Okay, now in number 5, I see that I have two different trig functions here. And even if I add the 3 over, I can't really factor this because there is no GCF here to take out, so I can't turn this into a product. However, I do recognize that cosine squared theta can be rewritten as 1 minus sine squared theta. Okay, so that's nice because now I have it in terms of just one trig function here. So I'm going to add the 3 over to the other side and simplify this. And I'm also going to change the entire expression. I'll factor out a -1 on both sides here so that I can write this as, whoops, that's going to be a 4 now. So that I can write this as sine squared theta minus 3 sine theta minus 4 equals 0. Now this expression here is a quadratic-like function. Okay, so I can factor that like I normally would with a quadratic. So and if you're not recognizing this, I'm going to make the substitution that sine of theta equals u. So I have u squared minus 3u minus 4 equals 0. So that's what I mean about it being quadratic-like. So you can factor it just like you would a normal quadratic. So I'm going to erase this real quick. So sine squared theta minus 3 sine theta minus 4 can factor into the sine of theta minus 4 times the sine of theta plus 1. So now I've just turned this into a product, so I can use zero product property now. So I have the sine of theta minus 4 equals 0, and the sine of theta plus 1 equals 0. So from here I get two different equations that I need to solve. Now, the sine of theta equals 4 is going to be another equation that has no solution to it. So I kind of glossed over that in the first example, but let me explain why that happens. Now, if you graph a sine function, you can even see graphically why this occurs. Our typical sine function here, it goes from -1 to 1. That's our range. So the sine function will never equal 4, which means that it'll have no solution. Okay. Now, using a graphical approach here to solve sine of theta equals -1, sine of theta equals -1 right here at 3/2 pi. Okay. So we've got, for part A here, from the domain 0 to 2 pi, right, we have 3/2 pi as a solution. For part B, if we want to include all real number solutions, and sine of theta is it has a period of 2 pi, so that means we're going to take 3/2 pi and add 2 pi n or 2 pi k, and that represents all of the real number solutions. Now for part C, to verify that with a calculator, again, if I try to type in the inverse sign, so sorry, let's go back to this. Algebraically, we take the inverse sign on both sides here. Oops. So that should be inverse sine 4. Okay. So we get theta equals inverse sine of 4. If I type that in, I should get an error message because that's not within the domain of your inverse function. See how it says error domain. Now for this other one, if I type in inverse sine of -1, I get an answer in -1.57 radians. Okay, so my mode is in radians right now. Let me just verify that real quick. And the reason why it's giving me this output here, it's not giving me a positive, that 3/2 pi that we saw within our the interval here that they're giving us 0 to 2 pi. The reason why we're seeing that is, again, the inverse sine function has a domain of negative pi over 2 to pi over 2. So even though, this is really the solution on that unit circle that we want, right, the 3/2 pi, it's giving us in terms of negative pi over 2, right? That is the same coterminal angle as negative pi over 2, and these are equivalent. 3/2 pi and negative pi over 2. So that's why our calculator isn't really that great to rely on, but it is something that you can use to verify your solutions. Okay? Okay, we're going to end the lesson now with a discussion on extraneous solutions. So remember, whenever you're solving, even any equation, and you use some algebraic techniques like squaring both sides of the equation, you run the risk of introducing extraneous solutions. They might work with the new equation that you created, but they don't necessarily work with the original equation that you're given. So I've got a couple examples here. One's going to be a little bit different than the other, and we're going to see that we end up with extraneous solutions that when we test back in the original equation, they fail. So for example here, I have the cosine of x times the tangent of x, which I will rewrite as sine of x over cosine of x, minus the sine of x times the cosecant of x, which I'll write as 1 over sine of x. Now just by canceling, I end up with sine of x minus 1 equals 0. This is pretty easy to solve. I end up with x equaling pi over 2. So the sine of x is equal to 1 at pi over 2, and since it's got a period of 2 pi, I can write that as plus 2 pi k, or 2 pi n. Okay, now, normally we'd say, okay, great, we have a solution, but you have to be careful here because at pi over 2, the tangent of x is actually undefined. So tan of x is undefined at pi over 2. Remember, when you graph the tangent of x, you end up with asymptotes at pi over 2 and multiples of pi over 2. So therefore, this equation actually has no solution, even though the equation that you manipulate it to become, sine of x equals 1, even though that has solutions, they don't actually work back in your original. So this equation here has no solution. Okay, last up is number 7, and notice that we're now dealing with degree measures rather than radian measures. So the first thing I look at is to try to see if I can factor this expression, and I can't do anything even if I subtract the 1 here. I can't really factor this as it stands. So I'm going to square both sides of this equation because I know that if I FOIL this, I end up with sine squared t plus 2 sine t cosine t plus cosine squared t equaling 1. And because I have sine squared t equals cosine squared t, that 1 will now cancel the other 1 on the other side, leaving me with 2 sine t cosine t, which is a product, equaling 0. So that's good because now I can set the sine of t equal to 0 and the cosine of t equal to 0. Alright, now on a unit circle, the sine of t is equal to 0 when you are at 0 degrees, at 180 degrees, and at 360 degrees, but that's not falling within our interval, right? 360 doesn't count here. Now the cosine of t is equal to 0 at 90 degrees and at 270 degrees. So it looks like we have 4 different solutions here within this restricted domain. Now, the problem is that that doesn't necessarily work within our original equation. Okay, so we've changed that equation to look like this, which might have solutions here, all 4 of those, but the original might not, use all of those solutions. So let's check each and every one. So I'm going to take sine of 0 plus the cosine of 0 degrees and see if that equals 1. Well, sine of 0 is 0, cosine of 0 is 1, so that one does work. So our 0 degrees works. If I plug in 180, we know that the sine of 180 is 0, but the cosine of 180 is actually negative 1. So that does not work. So 180 degrees doesn't work right now. Let's test 90 and the 270. So let's say sine of 90 and cosine of 90. The sine of 90 is 1, the cosine of 90 is 0. So that one works. And if we try 270, the sine of 270 degrees, this is negative 1. The cosine of 270 degrees, that is 0. But that is not a true equation, so that doesn't work either. So our solutions are 0 and 90 degrees. So moral of the story, just make sure that you're double checking your solutions back in your original equation. Alright, that's the end of the lesson. Nice job. I'll see you guys tomorrow in class.